Hi, welcome back to Spring CS170. We're on to the last part of what we're going to cover for this week. So you remember from the schedule, we're covering chapters 4 and 9. So here we are in chapter 9. Okay, so there's a couple of different concepts here. This is basically some parts of like memorizing certain terms or vocabulary, and some parts of just understanding how things fit together. And this will be the last part of what will go into your first exam, right? So remember this, right? You have all of your white area up here. This is what will be covered for the first exam, okay? And then all this blue stuff will go into the second exam. So just for your reference. All right, so let's get on with it. Here's all the different terms. So you definitely want to understand these. These will definitely be on the exam, okay? There's a little bit more notes on this one. So if you might have noticed for the last chapter, I did actually do a print of both the regular PowerPoint plus also with the notes. It has like notes after it. So when you go into my folder, you'll see that. So yeah, let's go through these terms here, right? So you have, these are different parts of a computer. They call it cast of characters, right? But these are just basically the different components or things that you can associate with the computer doing something. So you have something called processor that basically executes the programs and instructions. Um, Sometimes you might call it a CPU, a central processing unit, um, but it's basically the brains, right? It's doing something to execute the programs that you're running on the computer. So the operating system is kind of something that is like the software that sits on top of like all of this hardware. So you have all of this hardware. There's like all these different pieces to it, right? And um, you basically have to know how to execute. And you remember early on in the semester, we talked about this idea of abstraction, where you have these different layers, right? So at the higher and higher up layer, you don't necessarily need to understand all of the different things at the lower layer to get certain things done, right? And so the operating system is one of those layers, right? It goes up from the hardware because as everyday user, you're probably not going to care about like the specific machine code or language to either operate the CPU, the processor, or how your computer is going to read different memory addresses, or how it's going to communicate with other components. Like none of that stuff you really care about, right? All you care about is like I tell the computer to copy a file to a new folder, or I tell the computer to load up a program or do something, that it does it, right? So that's part of what the operating system is going to handle for you. So you don't actually have to get involved with all of the underlying components or the hardware. And then software, some people call it application layer, but the software will basically sit on top of the operating system. Okay, so these are your programs. Um, you can call it, software is software, right? It's code, right? And there's different layers of that, and so you can look at it any number of ways, but essentially it's programming instructions that will be sitting and telling the hardware what to do, right? So on top of the hardware, basically. And then you have individual instructions, right? So at the lowest level, you have like all these different lines of binary numbers, right? Zeros and ones. That's going to be feeding into your processor and doing different things with it. One set of those instructions will be telling the processor what to do. One set of those numbers will be things that it's acting on, right? Maybe it's adding two numbers together or something like that. Okay. And then there's this idea of the fetch and execute cycle, right? So the fetch part is me going to get what I need to process, right? So I need to, number one, get the instruction for the processor to know what to do next, right? Otherwise it doesn't know what to do, right? So you have to fetch, the information to say, oh, I want you to add these two numbers together, right? And of course, you actually have to get those two numbers to add together, right? So that's part of the fetch. Then the execute is actually getting that information, getting those two pieces of information, doing the actual addition, and then sending it back out into wherever it's going to go to, right? Maybe it's going to write back to memory or something like that. And then memory, memory is where you store your information, right? There's going to be some bits of memory that's going to be storing the actual instructions or the program, and there's going to be some bits of memory that actually stores the information that you're going to be acting on, okay? And then hardware is hardware, right? That's the physical parts of the computer, okay? And so this is a little picture that kind of shows roughly what I was just talking about, but kind of visually here, right? Um, so here's like the processor itself, okay? And you can see here is like within what I was calling the CPU, right? The central processing unit. You have this control unit, and then you have your arithmetic logic unit, all right? And then you have what they call local memory. This is memory right on the chip. This is like your working memory. So it's very close, right? Physically, it's very close to here, so things move quickly. When it goes out to secondary storage, secondary storage could be other types of memory on the computer, but it's physically further away from the computer. So you may not appreciate it. It seems like a small distance to you, but actually it's a pretty big distance, and that adds up over time if you're doing a lot of work. Okay, so there's going to be a trade-off in terms of speed. Otherwise, you can say, well, let me just jam a whole bunch of memory onto here, right? But just from a real estate perspective, you can only put so much memory here as your working memory that's close to what you have to work on. So what happens is that they go out to here to get, number one, like I said, the memory to store what you actually have to do, like your program, and number two, the actual data that you're going to be doing stuff on. And then it puts it over here to your local memory and does some work, okay? And you have some input here, and then you have your output, okay? So however you collect this information, it's going to be something that goes into whatever you have to produce on your output. Maybe you're going to do some things to maybe make your picture lighter, right? So you have a whole bunch of like information coming in related to the particular picture you're processing, and you're doing an ad of +16 or something like that, and you're gonna put that to your output. Maybe it goes right directly to the screen. Maybe it's gonna go to another piece of memory to store in the interim, whatever that is. Okay. There's like this book here, or not book, some reading here. I guess I'm trying to think. I guess maybe I should put this as a link under resource, right? So I'll do that. I'll put that under my page so you can just click on it instead of having to type this over again. So I'll add this onto the resources. Okay. This just gives a little bit more detail and kind of rehashes what I just talked about here. Okay. So again, the central processing unit, right? You remember that from the other picture. And you have like the ALU, or the arithmetic logic unit. Right, this is your I/O, right? So your input and output, right? Obviously, you put input, like let's say your keyboard, your mouse. Your output could be like your printer, maybe something like that. You remember I was saying, like when you access some of these secondary storage, it's like a lot further away. So if you write something into a hard drive, like if it's really like a physical hard drive spinning around, that's a huge amount of time in computer terms to do that type of I/O, right? If you get into like, just memory, it seems like that should be faster, which it is faster, but still, it's physically off the chip, right? So that's a way. it takes longer. Okay, uh, and then this is random access memory. This is something that is faster than this, right? The storage device here. So this will be faster just because it's not a physical writing to and from a disk or something like that. It's memory. Uh, and so this will be the next fastest type of memory. The fastest memory, like I said, is the memory which they don't actually show here, but there is like local memory that's on the processor, the CPU, right? I guess you could call it the working memory, right? Uh, so that's the one thing that's not on there, which I think should be on here. That's what this thing is here. Okay, they don't show that here, but there should be this memory. That's the fastest memory. That's the working memory that they'll use. Okay. All right. So this goes back to the point I was talking about with um, abstraction. Okay. So so you break it down. There's like a cycle here, and you see the notes here. Okay, so you see this thing, it says a register, uh, registers. Uh, they don't, oh yeah, they do say it. So memory locations, right? So this is what I meant by local memory on the computer, right? Uh, so you should remember at this point, it's interchangeable. You call it register or local memory is what I call it. But it's right here, right? You see registers and memory locations, right? So these are memories that are basically, like I said, used for the CPU to do its current instructions, right? So it's using this information as the local, most fastest memory it can get access to do its work, right? Uh, and then once it's done, it will shoot out like to the other memory that's further away, right? So just remember when I say the local memory on the chip, you could also refer to it as registers, okay? So let me go back up here because I skipped over this. So here's the control unit. So that's where you have, it's basically, you can look at the control unit as the coordinator, right? So it's getting the instructions. Like I said, you have to know what to do, right? And then you have to get the data. So what are you going to do? What are you going to act on, right? And then you're going to, once you get those two things together, right? You get your program, what you're going to do, you get the data that you're going to act on, then you actually have to execute the instruction, okay? And then the actual thing that does the number crunching is the ALU, right? So that does the actual math, right? So you're gonna add two numbers together or something like that. Um, and you know, the actual, in this case, transformations or transfers, okay? Then registers, I just talked about, that's your local working memory. And then you have a thing called program counter, and that's basically like, you know, however long your program is. Maybe your program is 5 steps or 6 steps or whatever it is. You have to know where you are, right? So you execute one step, what do? I go to the next step, or maybe I have to branch off and go somewhere else, stuff like that. So your program counter is helping you to keep track of things, okay? Um, and so what does that lead to? That leads to this idea of the fetch, decode, and execute cycle. So you'll kind of see this as a highlight or summary, whatever you want to call it. This is an important concept, so understand what this is, right? The fetch, decode, and execute cycle, right? So the first part is the fetch, right? You have to get the instruction from the memory, and like I said, you have the program counters. You have to keep track of what to do, right? As you go into these instructions, one instruction at a time, okay? Um, and then the next part is to do the decode, right? Um, so you have to get the stuff into your local memory or register, okay? And then you have to do the execute, okay? So that's the idea of this fetch, decode, and execute cycle, okay? So highlight, make sure this is something that you know, but actually you should really know all of these different things, right? You have to know all the different parts here, and then know this whole cycle of going out, getting stuff, uh, prepping it, and then executing it, okay? That's the cycle. So this kind of breaks it out a little bit more detail here, right? But it's the same circular motion, right? See this repeat down here, repeat. So it's the same thing, right? It's like this circle here, fetch, decode, execute. And so it breaks it down like this, okay? So you have the fetch instruction, right? 5-step cycle, fetch instruction. You have to do a decode, figure out what you're gonna do. Then you actually have to get the data, like, you know, like I said, the two piece, let's say, I keep on referring to two, it could be something else, but let's say we're getting 2 pieces of data, right? So you're getting your data, and then what you're gonna do with it? You're gonna add it, you're gonna add 1 to it, whatever, right? And then you actually have to do the execute of the instruction, and then when you return the results, you're not gonna store it locally on the chip anymore, you're gonna, or the CPU, I should say, you're gonna store it like on RAM, or maybe you're going to output to whatever, like your monitor, or to secondary storage, which would be, let's say, a hard drive or something like that, your memory stick. Um, so that's how it breaks down, and then it just loops through. It goes to the next instruction, right? Because you have the program counter, remember that, right? So it's repeat over and over again, go to the next instruction, and so on and so forth. It's a little bit simplistic because, you know, there's obviously like a whole bunch of other different things going on, but this is like the best way to break it down, right, and summarize it. Okay. Let me see here. So I'm at the 16-minute mark. So I'm going to pause here and just say this is the lecture that focuses on this fetch, decode, and execute cycle, as well as introducing the basic components for the CPU. Okay? And then I'm going to come back and we'll pick up from there. All right, thank you.